Hello. My final project is a replication study of the paper Physics-Informed Neural Networks, a deep learning framework for solving forward and inverse problems involving nonlinear partial differential equations. Down at the bottom, you can see my citation for the paper. So, to start with the overview, physics-informed neural networks are neural networks that basically obey physical laws. So the paper being replicated, it's actually a framework for solving differential equations, partial differential equations of a specific form. A lot of times that form has to do with mass conservation equations or some type of conservation equation. So modern auto differentiation techniques are essential to making this framework work. So that involves using auto differentiation in either PyTorch or TensorFlow or a similar framework. So this paper does have an official implementation in TensorFlow 1, but my project is to implement it in PyTorch. And this is because TensorFlow 1 is pretty outdated and it's not as natural to understand as PyTorch. I actually had some trouble while implementing it because I was kind of expecting it to behave like normal object-oriented programming, and it didn't because TensorFlow 1 is based on computational graphs. So in this paper, there are two main cases. They're inference and identification. So inference is finding the solution and identification is finding the solution, but also learning parameter values while the solution is found. So this paper considers the Schrodinger equation, the Navier-Stokes equation, the Korteweg-de Vries equation, the Alan-Kanick equation, and the Burgers equation. The Burgers equation is the simplest of them and the smallest, so it's the easiest to train. I tried implementing some of the other ones, but they were really big and hard to train on my laptop, and it would have been really expensive to use AWS GPU instances because I would have had to develop my program on them, not just run it on them, because I would have to learn how to do GPU programming in PyTorch. So in this paper, I focus on the Burgers equation and I do both inference and identification for the Burgers equation. So the Burgers equation calculates the speed of a fluid given the time, the position, and the viscosity. It's parameterized by time and position, and viscosity is a constant. So there's a lot of related work. So there's been other work into solving the Schrodinger equation. So other neural network architectures are explored. One such architecture is using additional subnets. And this paper also considers more advanced cases of the Schrodinger equation than what's covered in the paper I'm replicating by Racy. So deep learning is also commonly applied to fluid dynamics, specifically using the Navier-Stokes equations. And there's a lot of papers that cover fluid dynamics and deep learning. So another paper that covers the Navier-Stokes equations shows that you can solve them using a really similar method to Racy, but instead of using multi-layer perceptron networks, they use convolutional neural networks, which is an interesting approach, and it kind of builds off the work presented in the paper that I'm replicating. Finally, this can also be applied to water science. So almost the exact methods used in the paper I'm replicating were used in a paper on water science and the Saint-Venant equations. So there's really a lot of different stuff that these methods can be applied to. So like I said, we're relying a lot on auto differentiation, and PyTorch has a function that can compute the gradients of a neural network. So the neural network in this paper uses a pretty simple multi-layer perceptron network, uses Xavier normal weight initialization and hyperbolic tangent activation function. The biases are initialized to 0. And the forward pass is basically just computed with matrix multiplication and element-wise matrix addition. and then applying that tangent activation function, which I'll show in the code later. So the main part of using the physics-informed neural networks is defining the loss function. So the loss function used in this paper takes the output of the neural network, and that's U. But then it also applies some functions to it. So the function for inference is the derivative of U with respect to t plus U times the derivative of U with respect to x minus a constant times the second derivative of U with respect to x. And then it's the same for identification, but you'll also see there are some lambda values in there. And those lambda values are learned as well. And then the mean squared error for U and the mean squared error for F are added together. And that's basically the loss function that needs to be minimized to train these neural networks to accurately generate data. So going into the implementation, PyTorch is really nice because you can use a lot of abstraction and object-oriented programming and inheritance. So this layer class inherits from the nn.module class. So basically you can see that I am initializing the weights as a neural network parameter, meaning that it's trainable. And then I'm giving them a Xavier normal initialization. Same thing with the biases, they're just initialized to 0. And then I'm actually defining the forward pass for each layer here. And you can see it's just pretty simple matrix multiplication, element-wise addition with the biases, and then applying a hyperbolic tangent activation function. So I can combine all of those layers into a multi-layer perceptron network. So there's 8 hidden layers in this network with an input dimension of 2 and an output dimension of 1. And then I can also define the forward pass. So it takes in x and t, which is what parameterizes the Burger's equation. It does some stuff with the lower bounds and the upper bounds, and then it loops through all of the layers. And it computes that forward pass for every layer, and eventually it returns the final value. Something interesting here is on the last layer of the neural network in the paper implementation, they did not apply a hyperbolic tangent activation function, but I am doing that, but it doesn't seem to significantly affect results. Then finally, I get to creating the physics-informed neural network. So before that was just defining a multi-layer perceptron network. This is where it really gets interesting. It's possible there are better ways to organize this, but this works for now. So basically I pass in all of the training data and all of the evaluation data, so I can handle all of it in this one class. And then I save it to class level variables. Some interesting things here are I'm defining the model as my NN class. I also have a graphing class just to keep track of the loss values and the lambda values. And then I'm setting up a LB-FGS optimizer. The hyperparameters here don't exactly correspond to the hyperparameters in the paper, which could explain some small differences in model performance. Now here's the loss function, which is really interesting. So at the top, it's just making sure everything is a tensor and it requires gradient so that we can compute the derivatives. And then upred is basically the passing it, it's basically U, so it's passing it through the net and not really doing anything with it. That's the final value. And then below that, I have the calculating the function f. So you can see here I'm computing gradients. du dx, du dt, second derivative of u with respect to x. And then that all goes into this function here. Now, this is for inference. If it was for identification, I would also have lambdas, and I would replace this new here with a lambda. Then I compute the loss. which is just mean squared error of u plus mean squared error of f. So the training loop is also really important. So this training loop is actually for identification because it was more interesting. So for inference, I only use the LB-FGS optimizer. But for identification, it actually uses 10,000 iterations of Adam before applying the LB-FGS optimizer. So Adam kind of gets it close to the optimal value of the loss function, and then LB-FGS really just finalizes it and makes sure that the loss function is as optimized as possible. So you can see here that I'm keeping track of the loss values and the lambda values. Then I'm stepping the optimizer, the Adam optimizer. And then once that's done, I apply the LB-FGS optimizer, which is what this closure function is for, because the LB-FGS optimizer works a little bit differently than Adam. So here are the results for inference. So the loss function was optimized to a really small value, and it took about 35 minutes to train on an AWS instance that had 64 virtual CPUs. And the error was like 0.004 or about 0.4%. So really small error. The model's performing really well. The official implementation did a little bit better, but this is pretty good. And any differences are probably just due to hyperparameter tuning. So here I can see the predicted solution. So the figure on the left is the predicted solution for all values of x and t. And this really closely corresponds to the figure in the paper. But the figure on the slides is the one generated with my program and my generated data using my neural network in PyTorch. The figure on the right is also really similar to the figure in the paper. So it's just showing the value of the function u at a specific value of t. In this case, it's 0.5 for every value x. So the blue is the actual values and the red is the predicted values. And you can see that they match up really, really closely. So this model is performing well. So here's the loss values over time. So for inference, I'm just using LB-FGS, and it's a pretty smooth curve. It just generally tracks downward and eventually gets minimized really well. So identification is a little bit more interesting. So the loss actually gets minimized to a really similar value. And it also takes about 35 minutes to train on the same AWS EC2 instance. The error for u is pretty similar. It's also really good. And then lambda 1, the value is 0.999, and the actual value is 1. So this has a really small percent error. The value for lambda 2 is 0.0032. And this is also really close to the actual value. I have the actual value noted later in the slides, but it's 0.01 divided by pi. And it's really close. You can see there's a 0.66% error. So identification also performs really well. The actual paper performs a little bit better, but again, it's probably due to hyperparameter tuning. So I have really similar figures. It's also the predicted solution, and these also correspond very closely to the paper, although these figures in the slides are generated using my PyTorch code. This is the convergence. So it's the plot of the loss values over time. So up to 10,000 iterations, the Adam optimizer is being used. And it kind of jumps up and down a little bit. And that's probably because the optimizer is finding its way out of local minimums. And then around 10,000 iterations or parameter updates or epochs, doesn't really matter what you call it that much, because For each iteration, all of the data is being passed through, so it's a full batch. And once all the data is passed through, the parameters are updated. So after 10,000 iterations or parameter updates, LBFGS takes over and the curve gets a lot smoother, and it minimizes the loss function quite well. So these are the lambda values over time. So up until when BFGS takes over, and even a little bit after, these plots, they're a little jumpy, I guess. So the lambda values change, but eventually they converge very well to the actual values. So for lambda 1, the actual value is 1.0, and for lambda 2, it's 0.01 over pi, or about 0.00318. So you can see they converge really well. So for discussion and lessons learned, these physics-informed neural networks are very sensitive. I spent a lot of time debugging these neural networks, and I had some really simple mistakes that just caused them to entirely not work. Like I was multiplying by lambda times nu times the second derivative of u with respect to x. And it should have just been lambda times the second derivative of u with respect to x, and that was completely throwing off my model. It's just really simple things can make it not work. So you have to really fundamentally understand how these neural networks work and how PyTorch works, or your framework of choice, to make them work the way that they're supposed to. So they have many possible applications, from anything from quantum physics to water science. So it's a really exciting field. There's a lot of potential with physics-informed neural networks. Modern frameworks like PyTorch and TensorFlow are very powerful. You actually, in doing something like this, you can't use a lot of their higher level abstractions. Like I originally tried implementing in TensorFlow, and I tried using Keras, and that was just too high level to be able to do what I wanted to do here. These frameworks also depend on optimizations. So something interesting is I actually tried training the model on an AWS Graviton instance, which is their own processor, but it doesn't have the optimizations that PyTorch does for Intel processors. So I wasn't getting very good CPU utilization, even though that instance had more cores available. So that was pretty interesting. Like I said, I used AWS to train the models, so cloud services or GPUs are super important to training these neural networks efficiently. Finally, the Burgers equation is a pretty simple case of a physics-informed neural network. The Schrodinger equation and other equations are much more difficult to solve. A big part of that is because they have more data, and the networks are also bigger. So each layer in the Schrodinger network has 200 neurons, which just causes a lot bigger weight matrix. And the loss functions and everything else are just a lot more complicated. So they're a lot harder to implement than the Burgers equation, and a lot more expensive too, because you have to pay for cloud resources and GPUs. So in conclusion, this was a really interesting project. I'm just a master's student and I'm graduating, so I won't really be using this in research immediately, at least not academic research, but I am interested in working as an AI engineer one day. I plan to continue learning about neural networks and physics-informed neural networks after I graduate. And this class was really good for that, because before I took it, I didn't understand how to use PyTorch and TensorFlow. And learning these frameworks has given me the tools I need to continue learning about deep learning on my own. To continue this research, I'd really like to work on implementing everything in this paper. And for that, I probably need to buy a GPU. So I'm hopeful that in a year or so, maybe I can afford to buy a GPU and continue working on this project and learning more about neural networks. Here are my references, and thank you for the great class. I learned a lot.